there's no way that we can actually learn it, right, on Blackboard because the math is too, like the functions are not easily to, but, right, so I mean you have your nodes, so if I have 2 hidden nodes, for example, and I have 1 output, for example, there's 2 steps, right, 3 steps. 3 steps? Yeah, so you go through data, right, and for x, y, or inputs, outputs, in data. So by the way, right, I mean the textbook has backpropagation in it, right? It's got a complete pseudocode of the algorithm. So even if you didn't have
page 724, but it's a little tricky.
So it's more general than what I presented in class.
Yep.
It's really funny. I have gotten complaints that this class is too mathy and complaints that the class is not mathy enough. So I think that is
what I'm thinking is just
because I have tried really hard to be as little mathy as possible.
Not like
I think it was great because we just talked about data science. We have problems and they ask us to
actually how I learned from this class, I learned from doing. I implemented something, and then if I got that, it definitely will
I agree.
understand that.
So anyway,
so for each pair, right? So I'm going to do something. I'm going to do is I'm going to compute the activation values. Compute activation values for every unit. So what that means is, right? So if I have so if my data is like 1 0 1 0 1. Actually, let's make 2 output nodes. Fun. So I'm going to do addition, right? So notionally what I want to have is 2, but that doesn't make sense. I need bits. So what I'm going to have is I'm going to have the sum, and I'm going to have a carry. So 1 plus 0 is 1, carry of 0. These all are carry of 0, but this is carry of 1. All right? That's what I'm trying to learn. Okay, so we'll say this is the sum, this is the carry, not the lot. Okay, so what I'm going to do is I'm going to compute the activations. So if I'm looking at this example here, the activation of the input units is just their values. All right? Now, the activation of the hidden units is I take the linear combination of the weights and the inputs to this unit, right? So this is W1, W2, W3, W4, great numbers. Actually, let's call it maybe C, D. So A, B, C, D. So this is going to be what? It's going to be A times 1 plus B times 0. And then I've got to compute the activation function of that, right? So sigma of that. Right? Okay, so I got to compute that, so that's some number. And then I can do the same thing over here, right? So this is going to be sigma of 1 times C plus 0 times D, right? Okay, so that's some number. And then I do the same calculation on the end, right? So I've got 4 more values, 4 more weights over here. So E, F, G, H. And then so for this guy, I say C times, so let's give this a number. Let's call this X and let's call this Y. So that would be C times X plus G times Y, and then sigma of that. And then the other one is sigma of Fx plus Hy, right? Okay, so now I've computed the activation values of this. Now what I do is I say, okay, that's my current guess. So I have to figure out where am I wrong. So I compute my errors. So the errors are always going to be this sort of funny derivative thing, right? So you have to have the derivative of the activation. Well, handily, the derivative of this is just it times sigma of x times sigma of 1 minus x. So, so the errors for the output units are so okay, so
one
what,
minus
yeah. So if I call this, I don't know, if I say this value is z and this value is w, right? So okay, so so it's the actual error is say for this example z minus 1, right? That's the actual problem, and then times the activation, which is z, no, yeah, times 1.
So it was 1 minus z. Oh yeah, there we go.
Yeah, right. It's got all of them. Yeah. Yeah, is that right?
Why z minus 1?
So this is the difference between the correct value and the prediction, right?
Ah, okay. So hold on. This is
the one is going to be
which
correct
one is the
value.
prediction. I'm sorry. Prediction is z or prediction is
The prediction is z. right? The
Okay.
prediction is the activation value of this unit.
So that's gonna be a negative number? I mean,
It's never going to be negative. Can't
Oh.
be negative. Oh, that's going to be negative? Is it y minus x? It might be y minus x. I'm trying to, I forget what the sign is off the top of my head. I think it might be this way. So it could be negative, right? So if y was 0, then this could be negative. But in that way, that'll be positive. So it depends, right? You want to make sure that you add something that adds up. Never mind. Okay, so we calculate that for this guy, and then the other one, the other error of that guy is, so 0 minus w, which is times w times 1 minus w. Okay, and that's the error for the carry. And then you have to figure out what's the error for these guys. So this is a little more complicated. But what you do is you take the errors of the output and then you propagate them backwards. So the error for this guy is going to be x times 1 minus x times the sum of c times the error for the sum plus f times the error for the carry. Error for the carry. And then that, that's sort of the contribution of the error of these guys that comes from this node. And you do the same thing. You calculate the contribution of the error that comes from this node. So you calculate that contribution of error for all the hidden nodes. And then, and then at that point, you've got an error for every unit.
In the hidden net.
In both, in the output layer and the hidden layer. Everything, the inputs don't matter, but you've got an error for every other node. And then all you do is you take your errors and you multiply them. You say, okay, well, look at the weights that I already have and add in the inputs times the weights. So what I'm going to do is suppose if the error for this is error of x, what I'm going to say is a plus equals 1 times the errors of x, and b plus equals 1 times, or 0 times the errors of x, so that's not going to change. And then I do the same thing for the outputs, except the inputs to the outputs of the hidden layers. So so for if this is error sub z, the inputs to that node are c. No, that's not right. What is this? This is an e. Sorry. So e plus equals x times the error sub z, and what's the other one there? That's a g. So g plus equals y times the error sub z. So you're just combining the errors that you've figured out with what was the value that caused that error. So the way to think about this, right, is your input sort of propagates from left to right, activating all the nodes to some degree, right? Your neurons are getting information from the outside world, and they're reaching some level of activation. And then you figure out they're wrong. You figure out how much they're wrong, and then you look at the sort of cause of that error, of that activation, and you adjust your weights based on the combination of the error and the cause. And then you just keep doing that till it converges or till you're tired.
Nice. Wow, yeah, that's a really good overview.
Yeah, so again, the book has
Thanks,
this algorithm in detail, and you can go through it, but it's a little bit, it's more general. So the book's